know the physical property of water. In this case, we know we can use sun's heat to evaporate. Or in a lab, we can distill or evaporate in a beaker, leaving the salt. Now we're going to go into more details about atoms. Like we said in previous slides, atoms are smallest particles that can participate in chemical bonding, are the smallest particles in matter that take part in chemical reactions. But atoms are not indivisible. They have subatomic particles. When Dalton came up with his atomic theory, he thought atoms are indivisible. Ultimate particle, that's what atomos means in Greek. But we found out that atom has subatomic particles. If you think of an atom, it can be like solar system analogy, not exact analogy. Nucleus is the sun, planet rotating around the electrons. So that's kind of a nuclear model of atom. Protons and neutrons are in the nucleus. The protons have one positive charge, neutrons has zero charge, neutral. Electron has equal but negative charge to that of a proton. Mass of a electron is 1,000 times less than a mass of a proton, 10 to the negative 4. Mass of a proton and electron are almost equal, but neutron has some slightly larger mass, 1.0087. Reason for that we can explain now. Neutron could be formed by capturing proton and electron. Proton plus electron become that might be the small heaviness in a neutron is coming from captured electron by a proton. Protons are in the nucleus, neutrons are in the nucleus, electrons are outside. We think planetary model for atom, which is we're going to say is not a same as solar system with the nucleus being the center of the atom and electrons moving around like planets. It's not a correct model. Electrons in an atom behave as waves. We're going to look at wave shapes, which are called atomic orbitals later. Relative size of atom, nucleus, and atom. Atom is about 10 to the 10 meters. Negative 10 meters. 10 to the negative 10 meters is the size of an atom. Then 10 to the negative 14 is the size of a nucleus. Nucleus has a higher density. Most of the mass is in the nucleus. There are a lot of space that electron occupies around the atom. Therefore, mostly mass is within the nucleus. The electrons contribute very little mass to the mass of the atom. So we write down atomic symbols, like I said, first letter of the English name or the first and second letter in small case, like cobalt. Cobalt is CO because carbon use C already, it has to come up with a different symbol. Mass number of an atom is the number of protons added together, sum of the number of protons and neutrons in the nucleus of an atom. Mainly, protons and neutrons determine the mass of the atom. Atomic number is the number of protons in the nucleus. Protons number is also atomic number. It is also same as number of electrons in a neutral atom. So for example, we write down symbols, expanded atomic symbol, 12 as a superscript, 6 as a subscript. 6 is the atomic number, 12 is the mass number. Therefore, 6 protons from the atomic number 6. 12 is the sum of 6 plus 6 protons and neutrons. This in a written form, this isotope is called, this symbol is called carbon 12. We write the name of the element and the mass number, carbon 12. It's an isotope. For carbon also has carbon 13, atomic number is the same. Carbon 13 has 6 protons and 7 neutrons. So atomic symbol could be written for the element, just a plain letter symbol, or isotopic symbol showing the mass number and the atomic number. Isotopes are atoms of the same element which have same number of protons. An element is decided by number of protons in the nucleus. Carbon always has 6 protons, but they can have different number of neutrons. Carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. Carbon 14, which is a radioactive, has 6 protons and 8 neutrons. Most elements found in the periodic table found on Earth are mixtures of isotopes. For example, chlorine is chlorine 35 and chlorine 37. Chlorine 35 had 18 neutrons and chlorine is atomic number is 17. Chlorine 37 has 20 neutrons. So 37 minus 20 is 17. But these two isotopes are in the ratio of 75%, 75.77%, and 24.223%. Therefore, we had to calculate atomic mass, average atomic mass based on isotopes. The atomic mass reported in the periodic table is the weight average of masses based on naturally occurring isotope of an element. So how do you calculate the average atomic mass? There are two isotopes. Isotopic mass is 34.97, which is the 35, chlorine 35. Isotopic mass is coming from experiments. You can calculate the isotopic mass. Chlorine 37 is isotopic mass is 36.97. It's very close to whole number, but there are specific numbers multiplied by abundance. Chlorine is 75, chlorine 35 is 75.77 divided by 100 multiplied by isotopic mass plus abundance of chlorine 37 divided by 100 multiplied by isotopic mass. So we get the answer rounded off to 4 significant digits, 35.45 in this case. The mass reported in the periodic table is much more, have more significant digits because the accurate numbers, accurate weights are used than we use in the calculation. If you look at the periodic table, chlorine is 35.4527, which is the atomic number given there. So different elements have different atomic masses, atomic weights based on isotopic distribution. You can calculate if you are given, you can calculate the isotopic mass if you knew the atomic weight. You can calculate if you are given isotopic mass in natural abundances percentage. So this is how we calculated chlorine again. 34.97 is the isotopic mass of chlorine 35. 36.97 is isotopic mass of chlorine 37. That two multiplied together gives 75. As a fraction, it is 75.78. As a fraction, chlorine 37 is 0.24. So you can multiply fractions directly without. So in the previous slide, where we divide by 100 is to convert it to a fraction. The fractions are equal to total. So when you multiply isotopic mass in fractional mass, fraction of composition in fraction, so we get the same answer, rounded off to 35.45. Okay, I'm going to all right. we were talking about last item we talked about was how the atomic masses are calculated in the periodic table from the isotopic masses. So we went over that. And before that, we covered the material about generally about chemistry and sciences, scientific method, Dalton's atomic theory, and classification of matter. So we're going to continue from next slide. This one. Okay, there are atoms with different masses of the same element is called isotope. Lead 208 is an isotope with total mass number. Protons and neutrons are 208. So you need to know how to get the number of protons and neutrons from different isotopes. Normally, lead 208 is written as lead on the left side, superscript is 208, mass number. Superscript 208, lead. So once you're given lead 208 or at isotopic symbol 208, superscript 208 lead, you can get the number of protons. Knowing the element is lead, you can go to periodic table and look at the atomic number. For example, if you go to periodic table, if you expand on that, lead is 82 here, 82. Can you see 82 here? Right there. So for any element from the periodic table, you can get the atomic number. So once you get the atomic number, 82 for lead, there are 82 protons and 82 electrons, same number as protons and electrons, same as atomic number got from the periodic table. The 208 is mass number, sum of neutrons and protons, number of neutrons and protons. 208 is the sum. So if you subtract protons, 82 protons, you get rest of the remainder is 126 neutrons. So you can get the, excuse me, you can get the number of neutrons, protons, electrons from the name given as lead carbon 12, for example, lead 208, or atomic symbol of the isotope. The mass of lead atom is very small. It requires 10 to the 24 atoms of lead to make 1 pound. Therefore, we cannot see small atoms. We have to get large number of atoms to see it. Even one gram would have large amount of atoms. The diameter is in 10 to the negative meters of any atom. Is around 10 to the negative meters. Virtually all of the mass of atom is concentrated in nucleus because nucleus contains protons and neutrons which have higher masses, much more higher mass than electron. So mass is mainly coming from neutrons and protons. The diameter of a lead nucleus is 10 to the negative 14. All the nuclei are in that range. 10 to the, only difference is 1.6, could be different for different elements. The density of the lead nucleus is 10 to the 14 grams per cubic centimeter. This is a very highly dense. So the nucleus is the densest place in an atom. So we finish describing subatomic particles and their components, electrons and protons and neutrons. Now we're going to see the classification of elements. One of the ways to classify, list or classify elements, which are about 114 or 112, is to put them in a table. The one we call is a periodic table. You see, it is a table initially made by Dmitry Mendeleev. He arranged elements in the order of increasing atomic weight, beginning with hydrogen. Now, the atomic weight is roughly equal to half of the atomic weight. Half of the atomic weight is roughly equal to atomic number. Therefore, it's coincided with the current modern periodic table, where the atomic weight is replaced by atomic number, beginning with hydrogen. He observed when elements are arranged in this manner, certain set of properties recur periodically. Okay, you have a question? Okay. When we arrange elements in the periodic table in a manner, the properties will recur. That means repeat periodically. I'm going to show its periodicity in the groups in a minute. He then arranged elements with recurring set of properties in the same column. So the columns in the periodic table have chemicals with same chemical properties, elements with same chemical properties. For example, lithium, sodium, potassium fall in the same column and start the next column. Column has periods. Lithium in the second period, sodium is the third period, and potassium is in the horizontal row, fourth row. If you look at this, that's a Mendeleev modern periodic table that came after Mendeleev. So this is a table. The main table is in the middle, just arrows describing are not the part of table. The captions with arrows are just the descriptions. So therefore, basically, this whole table in the middle is, and two rows at the bottom are periodic table. So you have columns, 18 columns. If you look at the number 1, 2, 3, 4 numbers in parentheses, up to 18 columns are called groups. So vertical columns in the periodic table are called groups. Horizontal rows there are 7 of them, 1, 2, 3, 4, 5, 6, 7, are called periods. So groups have elements with similar chemical properties. So if you go with lithium, after you go on over period here, come back to here, have the same chemical properties. Magnesium, if you go through here, a period is going from that to the bottom of it. So there's a periodicity in the chemical properties of a group. So Mendeleev arranged elements according to the chemical properties, similar chemical properties, to have similar chemical properties in a group. We're going to look into this again. So the group 1, or is also called 1A in the earlier notation. Sometimes we use group 1 as 1A, group 2 as 2A. The tall columns, which are in orange or dark brown, the light brown, are called main groups. Main groups are within the orange color, main groups. The columns 3 through 12, up to 12, are called transition elements. And they are designated as 3B, after 2A, 3B, 4B, 5B, 6B, 7B, 8B. Sometimes we call it 9. 8B consists of all the elements in the 9, 8, 9, and 10 periods. 1B is group 11, 2B is group 12, like that. We normally use the numbers at the bottom as group numbers 1 through 8 for columns. For periods, we use numbers 1 through 7. There are 7. Now there are 2 rows of elements at the bottom of the periodic table. They're called lanthanides and actinides. Why are they there? The reason for that is to keep up the periodicity, to have elements in the same group or column, to have similar chemical properties. If you put them in there, the atomic number from 58 to 71, it should go here. That will disturb the periodicity. So here also, actinide, you go through 50 to 103, then start with 104. Because they are removed from the periodic table to keep the periodicity. These 2 rows are called actinide elements and lanthanide elements. Okay? So the certain groups have specific name. Group 1 or 1A is called alkali metal. Group 2 or 2A is called alkaline earth metals. Group 17 is called halogens. Group 18 is called noble gases. In a box in the periodic table, it contains an element. Each box has different elements. The first box here is represented here. The first number on the box is called atomic number. It's the number of protons in the nucleus. The second symbol, the second letter given as a symbol, is the atomic symbol for the element. Hydrogen is hydrogen. The third number is the atomic weight, calculated by taking the average of isotopic masses. We calculated that for chlorine 17, remember in the previous slide. So you have a brief introduction to periodic table now. Apart from groups, there are blocks of elements called metals and non-metals in the periodic table. Non-metals and metals and non-metals. Metals are the elements which are solid at room temperature except mercury. They have specific properties. Metals are shiny, conduct electricity, and they're ductile. They could be hammered into different shape, malleable. They form alloys. So brass is a compound alloy of metals are called compounds of two different metals are called alloy. Copper and zinc as a mixture, homogeneous mixture of copper and zinc is called alloy brass. In chemical reaction, metals tend to give up electrons, therefore they make positive ions or cations. Non-metals, except hydrogen, they lie in the right side of the periodic table, except for graphite, do not conduct electricity. They tend to accept electrons. Let me show you non-metal metal line here. So in the periodic table, the green ones are the elements in the green boxes are the metals. In the blue boxes these are called non-metals. Metals include that lanthanide, actinides. Hydrogen is even though it's found in among metal group, it's not considered a metal. Hydrogen is a non-metal. So these have different properties. The elements in between are called metalloids. Metalloids are the 7 elements: boron, silicon, germanium, arsenic, stilbium, tantalum, and tellurium and astatine. Okay, so they have classification is based on, except hydrogen, non-metals, they lie in the right side of that's in the blue boxes. Except graphite, they don't conduct electricity. Graphite is the only one that conducts electricity, non-metal. They tend to form anions, negatively charged ions. Metalloids are the 7 I've said that is in pink boxes. In the middle, boron, silicon, germanium, arsenic, stilbium, and tellurium. Antimony is called, stilbium is the Latin name, antimony. Metalloids have, can you turn off your phone? Somebody got a, okay. So, somebody has an open mic. Tanya Moore, turn off your mic. Okay. I turn off the mic, it's making noise. All right. Let me see if I got that. See, certain things like that happen. It's always difficulties. It just diverts the attention of the class. You understand what I mean here? All right. Metalloids have some properties of the metal and some of the non-metals. For example, they are shiny like metals, but unlike metal, do not conduct electricity. So boron, silicon, germanium, and arsenic. Some of them are semiconductors, such silicon and germanium. One of the metalloids, silicon, is a semiconductor used in computer chips. It does not conduct electricity under certain applied voltage, but becomes conductor at higher applied voltage. So they could be doped to increase their conductivity. Silica is doped with trace metals to use in computer chips. So we are going back to periods in the periodic table. As I discussed before, properties of certain groups, alkaline metal, it's a group 1, very reactive, except hydrogen, make positive ions, react with oxygen to form compound that dissolve into alkaline solution in water. They form metal oxide like potassium oxide, sodium oxide. When they dissolve in water, they form alkali solution, alkaline. That means basic solution. Alkaline earth metals is a group 2 or group 2A reactive. So we start with group 1, 2 reactive metals. They form, you can tell group 2A always make positive 2 cations. Group 1 make positive 1. They react with oxygen to form metal oxide and strongly alkaline, but only thing is, unlike the group 1A, they may not be water soluble. So that probably has something to do with having a positive 2 charge. Transition metals are the middle groups right here in the middle in yellow here. These are transition metals. Form ions with several different charges. They're called different oxidation states. So unlike group 1A and 2A have fixed charges, transition metal have 2 or more different charge numbers, cations, 1 or 2, 3, 4, 5, one of them. The lanthanide are the last 2 rows, first row of the last 2 rows, lanthanide and actinide. They are similar to transition metal. They tend to form positive 2 and positive 3 ions. They are metals. Lanthanide is atomic number is 58 to 72. Actinide is 90 to 103. Actinides are radioactive. Atoms with higher atomic number greater than 83 are radioactive. That means they decay. They release radiation. Group 18 or 7A is called halogens. They are reactive. They are mainly in diatomic molecules. Elements exist as diatomic molecules. They make negative ions like chloride ion, bromide ion. Chlorine with negative charge is called chloride ion. Then form salts. Salts are ionic compounds containing ions are called salts. With alkali metal like sodium chloride, sodium is alkali metal, they make compound salts. Group 18 or group 8A group is called noble gases. They are inert. They don't react easily with anything. Heavy elements have limited reactivity. Some of the heavy elements have some reactivity, do not form ions. They exist as monoatomic gases. Helium is helium, not helium-2, unlike chlorine-2, bromine-2. So these are some of the properties of groups in the periodic table. We look into this periodic table with non-metals, non-metalloids, and metals. And at the bottom are actinides and lanthanides and actinides. Atomic number 58 to 71. Atomic number actinides is 90 to 103, as we discussed in the previous slide. So I'm giving you exhaustive information. Metals have metallic property, conduct heat and electricity. Solids at room temperature. Chemical reactivity varies greatly. Some of the metals, like alkali and alkali earth metals, excuse me, are highly reactive. Some of the gold and platinum and transition elements are unreactive. So gold is a precious metal because it's used in coins and jewelry. Platinum is also used in jewelry. They are unreactive, therefore they have value as something that will not change and people make jewelry out of it. Non-metals are brittle. Brittle means break up. They are insulators, do not conduct electricity or heat. Chemical reactivity varies. Exist mostly as compound rather than pure elements. The non-metals like water, different ammonia, different combination of metal atoms, non-metals atom, they exist as compound with other pure elements. Many are gases, some are solid at room temperature. Only bromine is a liquid. Bromine is a liquid. They are gases, mostly other elements, non-metal elements. Metalloids are intermediate properties between metals and non-metals. Metallic shine, but brittle. Unlike metals, they have metallic shine, but they are brittle. They are semiconductors. Conduct electricity, but not as well as metals. Example are silicon and germanium are semiconductors. So halogen, if you look at the group 17, which are called halogen groups, there are 4 elements called halogens: fluorine, chlorine, bromine, iodine. They exist as fluorine exists as a gas. In that yellow gas, that the yellow gas is chlorine. Bromine is brown gas and a liquid also. Liquid at the bottom and some. Chlorine is definitely a gas. There's no liquid in it. Bromine is a liquid. Iodine is a solid. So iodine is the purple crystals. They have similar chemical properties like we described previously discussing periodic table. If you look at the physical properties, fluorine has lowest melting point, boiling point. And as we go down the group, melting points and boiling points increase because of the number of electrons. They have stronger electron attractive forces because number of electrons and the elements increase. They attract to each other through the electrons. So going down a group, melting point, boiling point increase as physical properties. Lithium also, group 1, elemental alkali metal, group 1A or group 1. They show other way around. Non-metals, melting point, boiling point decrease. If you look at this one, it decrease. Number decrease. This is kind of a boiling point increase. Negative number 188 and 133 is an increase. So that is different from what we seen in here. On the alkali metal, boiling point increase opposite direction from bottom to top. That's what I was trying to say. This is something to do with bonding, metallic bonds. Also, metallic bonds is different. CCM has lower melting point than lithium. So there's a opposite properties for these two groups as far as physical properties are concerned. On the other hand, noble gases show the same trend as bromine, halogen. They increase as going down. So that's what we saw in here also. Non-metals properties. So there's some periodicity or some trend in the periodic table you can use. Non-metals increase melting boiling points as you go down the group. Go down the group means going from here to here. Metals alkali metals melting points decrease as you go down the group. So noble gases behave like non-metals in as far as melting point description goes. Now we are going to look into chemical properties of we discussed the trends in physical properties, melting point, boiling point. Now we're going to look into electronic configuration of elements, chemical properties, to describe chemical properties. What is electron configuration? Electron configuration is the arrangement of electrons in the extranuclear space. So that means from the nucleus, how they are arranged outside the nucleus is the idea for electron configuration, how electrons are arranged in the atom outside the nucleus. The energy of electron in an atom is quantized, which means that electron in an atom can have certain allowed energies. So this is called quantum theory, quantized. That means only first electron have a certain energy, second electron have a certain energy, fourth electron has certain energy, increasing energy as we go add more electrons to atom. So there are certain energy levels starting from lowest to highest. So when you fill in the electrons to atom, you fill electrons to the lowest level, which is close to the nucleus. They're like orbits, shells. We call shells, orbits in the planet system are called shells. First shell has the lowest energy, second shell has the next energy, highest energy, so on, 3, 4 shell, fourth shell. The ground state electronic configuration is when the electrons are added to the lowest energy state of atom. So when you put electrons, we put it to the lowest energy level, close to the nucleus. Now, these ideas are going to be expanded as we go on. What you see is electrons are in quantized energy levels. These energy levels are called shells. The shells also have subshells. We're going to look into that. Electrons are waves, not particles. They have more wave properties. So electrons in a shell could be first shell, for example. Electron in the first shell is 1s. Electron in the second shell has 2s and 2p. 2 means the second shell. 1 in front of the s. S is the orbital. Orbital is the shape of the electron. So there are shapes of the electron for different orbitals. For example, s orbital have a spherical shape. P orbital has a dumbbell shape. D orbitals there are d orbitals on the third one. No, there are 3 p orbitals. 3 p orbitals. I'm going to talk about this again. Let's look at the electrons are wave shapes. They are found as s orbitals, p orbitals, d orbitals, and f orbitals. First one is S shape, spherical. Second one is dumbbell. There are 3 of equal energy in 3 different directions. There are 3 p orbitals, 1 s orbital. There are different shape for d orbitals and 7 orbital shapes for f orbitals. This will become very clear. You don't have to remember anything, only understand the orbital shape, orbital types is the one that is required you to do. Electron also has a spin. So electron has a orbital shape and a spin. Orbital shapes are shown here, SP, S, SP, D, F. Spin is kind of a rotation around the axis. All right. Now what I have described is electrons arrangement in an atom are in shells. A shell is same as period in the periodic table. This is a periodic table with Loam form where you have put lanthanide and actinides into the whole table. So what we know is this. When you're filling an electron to alkali metal and alkaline earth metal, the last electron added goes to, in an alkali metal, go to 1 s orbital, s orbital. So second electron goes to the s orbitals can have 2 electrons with spin, opposite spins. 2 electrons in a shell orbital can have electrons with opposite spin. So D shells are 10 of them. I talked about this. 5 of them here. Each place in the periodic table, these are orbitals, S, P, D, F. Each one can have 2 electrons. So S orbital take up 2 electrons with 1a and 2a. D orbitals take up 5 electrons here. F orbital take 14 electrons. And the D orbitals continue filling after F orbitals. And P orbitals are filled after F orbitals here. All right, after 3 D orbitals. Okay, there are blocks in the periodic table. Alkaline metal and alkaline earth, S orbital is the one is being filled first. The D orbitals in blue, there are 10 of them. There are 6 of them places or electrons goes into P orbitals. Why P orbitals have 6 electrons? There are 3 P orbitals. Each one can take up 2 electrons with plus or negative spin, opposite spins. Okay, this becomes much easy if you do a problem later. Okay, hold on. I'm going to talk about that using periodic table as a guide. Just hang in there, time being. So if you look at this, how many elements are in the shell 1? 1, 2. Shell 3, 1, 2, 3, 4, 5, 6, 8. Shell 3, 1, 2, I'm counting 1, 2, group, shell 3, 1, 2, 10, 12. 12 plus 6 is 18. If you count the electrons, this is how you got number of shells are 1, 2, 3. Lowest energy shell is the top, the bottom one, shell 1, shell 2, shell 3, shell 4. How do you get 2 electrons? Because in the periodic table here, expanded here, alkali metal, starting with shell 1, 1, 2. If you count the number of boxes, that's 8 on the second shell. Number 3, 18. Number 4, that's 18 also. So if you look at that, number 3. Okay, hold on a second. Number 3, I need to count it, right? Number 3 is here. Three, now only 4F is filled. Okay, how do I count? Number 3. Number of electrons shells can hold. Okay. $18 I counted. Number 3. Okay, I'm sorry. 3. 2, that 10 here. Number 3 shell has a 3, 10. Plus 6 is 18. Do you understand? You count all the 3 shells with the number 3, 18. Number 4, you count the 2, 10, 12. Okay, number 4. You count the 4D. 4 is number 4. And 4 is 14 of them. So 18 plus 14 is 32. So that's how you got number of electrons. I'm going to use this again. You understand? Different